Good morning, good evening. Welcome again to AI Foundations. This is Module 3, Introduction to Machine Learning, Session 2. We have Parul, Pandey, a data scientist, a Categorizing master, a blogger, a meetup leader. She will be leading us today. So with that, I'm going to hand it over to Parul and we'll get started.
Thank you, Rafael, and welcome everybody. I am Parul and I'll be your instructor for this course. And today we are going to take a notch into the second session of the Introduction to Machine Learning module, which is called Myth versus Reality, the Data Science Workflow Explained. So before we start, let's just quickly see what we have covered in the last session that was held on Tuesday. So we started a module and we understood what machine learning is from the business point of view and how we could frame business problems as machine learning problems. Let me tell you a little more about this module. So we've covered the first session. Today we are in the second session. Now this session will be followed by a study group and an AMA session on the weekends. So you're more than welcome to join and ask any questions that you have. And there'll be 2 more sessions for this module on the coming Tuesday and Thursday, again, which will be followed by the study group and AMA session. So let's begin. So what you can expect in today's session? Well, I'll start by giving a little primer on what machine learning is, and then we'll see what are the problems that could be solved by machine learning, what are the vital components of machine learning, how does a machine learning workflow is created, and end-to-end machine workflow, how is it created? And yes, and then we'll summarize everything and we'll close out. So let's start with machine learning. Essentially, let's have an overview of what it is. So we've been talking a lot about machine learning. We talked about it in the last session also. But today, we're going to touch upon some specific aspects of machine learning. So today, we are going to have a high-level introduction to the field of machine learning, including the broader context in which this branch of computer science exists. So machine learning, like I mentioned in the last session also, is a subset of artificial intelligence, and its focus is to create machines that can simulate human intelligence. So let's break that down little by little. So one of the important components of machine learning is that we take some data and we use that data to make predictions or identify important relationships in the data. Now, why do we need machine learning? Because like all of us are aware that data is growing day by day, and it is just impossible to understand all of this data with higher speed and higher accuracy by mere humans. We know that more than 80% of this data is unstructured. So that means it's either in the form of audio, video, photographs, documents. And if we have to find patterns in such data, it's very difficult for us. So we rely on machines. So this huge, massive data set is then fed into machines so that they could find some patterns from it in minimum time. Let's look at some of the common everyday use cases of machine learning just to get the things rolling. So spam filtering, I think all of you witness this machine learning use case every day via your inboxes. So of the email that is sent worldwide and the ones which are going to be sent over the next 24 hours, around 70% of them are spam. So spam stands for unsolicited electronic junk messages, which are not required. And spammers are always devising more sophisticated ways to actually get through into your inbox. But having said that, your inbox does a pretty good job in differentiating between the spam and the non-spam. And it definitely uses machine learning algorithms in the backdrop. Then we have credit default prediction. So again, machine learning is used by banks to predict which customers are going to default. Now, banks have this huge database of customers, and if they start manually looking through all the records, I think they won't be able to do a good job. In fact, they might have mistakes, but they rely on machine learning to find patterns in the previous data or the historical data of a consumer or a customer, and then they make predictions. So this is just an overview of some of the common machine learning problems that we encounter in our daily lives. So machine learning is again used in a wide variety of different scenarios. And machine learning coupled with deep learning is today applied in analytics, like for forecasting sales, forecasting stocks prices, classification, like differentiating a spam email from a non-spam email, then decision making, for instance, recommenders. So whether you should buy product A or you should buy product B, whether you should watch movie A or movie B. NLP, or you could say text analysis. NLP stands for natural language processing. So we have multitude of use cases in NLP, like sentiment analysis of the customers based on their reviews on social media, topic classification, translation, again, a very important aspect, and computer vision. Especially today, now we're hearing about things like self-driving cars, autonomous cars, object detection. So these are some applied use cases of machine learning and deep learning. And more on that will be covered in the next module, which is Introduction to Deep Learning. So this is just to give you an overview of the capabilities of machine learning. So now we have a fair idea about what machine learning is and what are the use cases. Let's start by categorizing the machine learning problems. So with this, we come to our second part of the session. Now, what kind of problems can be solved with machine learning? So there are three specific, or on a broader level, you could classify these problems under three categories. Either you find a category in a problem, or you find a number, or you find clusters or groups. So what do you mean by finding a category? Say, for instance, these are some of the data points that you have. Consider the yellow ones to be the positive tweets which have positive sentiment, which are written with some positive meaning. And the black ones are the tweets which have negative sentiments, and we know them. So you can see now our idea or our job as data scientists is to create a model which could separate both the tweets. Now it would search for patterns, inherent patterns in the data, and it would want to classify the tweets in separate categories. So the yellow ones should go to the positive sentiment tweets, and the black ones should go to the negative sentiment tweets. And let's say this is a classifier which has created a boundary between the two. Now you'll see that there are some errors. Some of the yellow points are coming into the black region, and some of the black points are going into the yellow region, but it's done a decent job. Now, if we get a new tweet and we do not know about that tweet, we don't know whether this is positive or this is negative, what this classifier tells us is that it is falling in the yellow zone, which means it is a positive tweet. So this is called finding a category. You find a category for a number, whether the tweet is positive or negative, whether the person is having cancer or not, whether the person is going to default on a credit card loan or not. Such problems are called classification problems. There is another set of problems which are called regression problems. And the idea in regression problem is where you have to predict a number. So for instance, you have to predict the stock price of a stock after 30 days. You have to predict the sales volume. So you need to predict a number or any time series correlation. So there you cannot find a category. You want exact numbers. What is going to be my sales after 30 days? So for such problems, what we do is we find a relationship between the variable that we have to predict and the variables that we have. So for instance, here we have a problem where we are given the height of students and we have to predict so there's a relationship between the height and the body weight. And we plot all these data points and we get a relation between it. So we get a relationship that the weight of the students is equal to 80 plus twice the height. So we have got a relationship. Now we can easily plug in the heights of the students and we'll get their weights. So here we find out or predict the weight of the students given their heights. So this is a regression problem, and this equation is a relationship that we get. A third category is finding groups or clusters. Now what happens is, in such cases, you are just given data and you have no knowledge about any historical relationship in that data. So what you do is you start finding subgroups. So for instance, you have this data set where you're given the width and the height of people and you create categories in them. So these are the people whose height is also more and they have less weight. So this should be weight actually. These are the people whose height is less and they sort of have weight in between, average weight. And this group of people have higher height, but they also have a higher weight. So here what you've done is you've segmented this data set into clusters, and depending upon these clusters, now you could do a lot of things, like you could do target marketing, you could market specific products to them, to this group and to this group separately. So you found a cluster and a group between a big data set. So these were the three kinds of problems, major problems that are solved by machine learning: classification, regression, and grouping or clustering. So now we have an idea as to what kind of problems, what kind of problems we can employ machine learning. And with this, let's get on to the third part, that's the components of machine learning. So there are three very important components of any machine learning problem that you would encounter. The first one is data. Data is everywhere, from customer experience, from real-time streaming. You are surrounded by data. And if we were to simplify machine learning problems, we could say that machine learning is using data to answer questions. So this, of course, is an oversimplification, but it can still serve a useful purpose. Data is a key to unlocking machine learning, as much as machine learning is the key to unlocking the insights hidden in the data. The more diverse the data, the better will be your result. Now, data is a very broad term. So what kind of data can you feed to a machine learning model? So typically, there are two sorts of data: a categorical data and a numerical data. Further, you could divide the numerical data as either being continuous or discrete. And similarly, the categorical data could either be nominal or ordinal. Now, what does that mean? This means that numerical data, as the name suggests, is any data where data points are exact numbers. So sales price, weight, height, and all the data in machine learning eventually ends up as numerical data. So whatever sort of data you have to make sure that you convert it into numerical data to be fed to a machine learning problem. Now this numerical data, since it's form of numbers, you could add, you could subtract, you could even compare this, like you could compare the height of two people, or you could even compare the incomes of two families. Now, numerical data can be further divided into either being continuous or discrete. Now, what does that mean? Continuous data is a data that can take any value. For instance, temperature. So temperature could take any value. It could be in decimals, it could be whole numbers. Similarly, weight. So your weight could be 26.3 kgs, 26.435 kgs, or 27 kgs. Discrete data, on the other hand, can only take certain values. For instance, your shoe size. So your shoe size could only be like 3, 4, or sometimes in some, I think, countries, it's 3.5, 4.5, but it cannot be like 3.4567. Similarly, number of people. Number of people can always be 4 people, 5 people, 100 people. They cannot be like 4.5 people. So that's discrete numerical data. Similarly, we have categorical data. So categorical data represents characteristics. So it could be player's team, a rugby player's team, or zip codes, or hair color like black, brown, white, gender, male or female. Now these numbers, now this categorical data can also be assigned some numbers. So for instance, you could assign number 1 to male and maybe 2 to a female. You could assign 1 to hair color black, 2 to hair color white, similarly. But these mathematical notations have actually no meaning because you cannot add them. You cannot add people with different hair colors because they don't make sense. Again, categorical data can also be divided into nominal and ordinal. So nominal data has no intrinsic order. So for instance, if it's gender, a male and a female, you cannot compare them. You cannot compare the postal codes. They are different entities, cannot be compared. But ordinal data, on the other hand, has some intrinsic order inside. Let's say there are students' grades, and the grading system says A for the best student, B, and then C. So this data is categorical because there are categories, A category, B category, and C category, but it also has an order where A is greater than B and B is greater than C. So that sort of data is an ordinal categorical data. So this was about the numerical data that we have. The other data that we can handle today is images data. We could feed in images. We could feed in videos, audio transcripts. We could have, again, text data for NLP or text classification. We have sensor data. We also have time series data. Time series data is a sequence of numbers which is collected at regular intervals of time, like stock prices or the rate at which COVID cases are increasing by month. So all these are time series data. So these are different kind of data that machine learning algorithms can handle very easily. But something very important to understand here is for images, videos, text data, ultimately you have to convert them into numbers to feed them into a machine learning algorithm. So this was all about data. So that was the first important feature of machine learning algorithm. Another important part is features. So what do you mean by features? Let's understand it through an example. Say you have to predict, so I'm using this example a lot just to make sure that you understand and you can relate to this example. So say we have to predict which customer will default on the credit card payment. Now, we have a person and we have to identify whether this particular person, say Bob, will default. So we try collecting some of the data points for Bob. Say we collect his age, what is his historical bill amount, how many payments he's made, and what is his account balance. And we collect all this data and we populate it into a table. So these four things, age, historical bill amounts, historical payments made, and account balances, together they constitute features. So these are the properties of the things that we are trying to learn about. And we are trying to learn about the fact that whether he will repay his loan on time or not. These are also called variables or parameters. So for instance, if your data set consists of emails, their features would be words of the email, to and fro addresses, maybe the subject line, maybe the length of the email, and so on. And when you store data into tables, like the example, these features are the column names. So you can see there are 4 features, and there could be many. So features are the properties of the things that we're trying to predict. And the last important thing, or the last important aspect of a machine learning is their algorithms. Now, what is an algorithm? If you go by the definition from Wikipedia, it says an algorithm is a finite sequence of well-defined computer implementable instructions, typically to solve a class of problems or to perform a computation. Now, what does this mean? So this means that algorithms are step-by-step instructions which are given to a computer to perform a certain operation. And there could be many types of operations that can be done. For example, here it is an algorithm that we have, which is y is wx plus b. Now, this is the equation of a straight line, if you could recollect. And what it does is, it calculates y from the value of x when w and b are given. But the question is, how do we know what is w and b? And here the algorithm, we have a set algorithm. Yes, we can find out y. We also have x, but then we don't know what w and b is. So how does a machine know what to do? So what we do in this case is, we create a data set. So what we do is, we know from our past experience that when x was 1, y was 2, when x was 2, y was 4, and so on. We know this. So what we start doing is, we start plugging in these values. And once we solve this equation, we get the values of w and b. Now, it's a very simple equation, and we solve it. Now, we know what is w and we know what b is. Now, let's say after some time, we get a value for x that's 5, and we don't know what y is this time. But using the given algorithm, y is wx plus b, we feed in the values of w, of b, and even x to get the value of y. And this essentially constitutes the learning part, learning from data. This algorithm learned the values of w and b from the given data set, and then it made prediction for a new data point that was 5. And this is how the whole machine learning concept works. So what are the kinds of algorithms that are used in machine learning? But there are many algorithms. To name a few, there are linear regression, and the one that I just showed you is actually a linear regression in working. There is also logistic regression, cart classification and regression trees, naive Bayes, KNN, PCA, GBMs, and there are many more. But more on this will be taken in the third session. So this is just to give you an idea about what different kinds of algorithms we have. And we have to choose our algorithms depending upon the problem that we have at hand. So just to summarize what we studied that the three important components of machine learning are data, features, and algorithms. And they together form the backbone of machine learning. So with this, we conclude the third part, and it's time to move on the final part, which is the machine learning workflow. We've been understanding all these concepts to finally understand how does a workflow, machine learning workflow work, and how is something that we're going to study here different from what happens in real life, hence myth versus reality. Okay, so this is a data science workflow, and it is the ideal data science workflow, which is also shown in a lot of textbooks. So you have various stages here, the data collection and preparation stage, then the data analysis and feature engineering stage, followed by the model training stage. Then you understand and explain, deploy, and monitor. Now, let's go over each of these phases in a little detail. Now, also one more thing before we go into detail is you have to keep in mind a very important thing. This figure is actually a typical process now, which might not be ideal for every project. So this process is not always sequential, which you will also see. You might, for example, split your data after you transform it. You might need to collect more data. You might need to modify the feature set even after training begins. And it's an iterative process. You have to get back sometimes to the previous stage before you go to the next stage. And let's see how. Let's start with the first stage, data collection and preparation. So what entails data collection and preparation? Data is a very important aspect of any machine learning workflow because what you feed in is a representation of what you will get ultimately. If you have insufficient data, if you have biased data, your model will also be a representation of that. You will have a biased model. So you have to understand the problem. And when you know what problem you have, you'll start gathering the data. Now, it is not that simple because you have to clean the data also. You might normalize the data. You might have to correct some of the errors. You might have to remove the noise from your data. You have to identify what are the features and what are the labels in your data. And sometimes if you just have one set of data, you would also need to split that data for your evaluation purpose. Let's see. So I touched upon features, the concept of features previously too, where I said features are the parameters. So what is label? Now you could see it's the same example that I have. So the features are the descriptive attributes, and label is what you are trying to predict or forecast. It is also called target. So what essentially happens is you collect historical data, and that historical data has labels. Now, this I'm talking for a supervised machine learning problem. Again, machine learning problems are supervised and unsupervised. So for the time being, you can just understand that supervised machine learning problems are the ones in which the label has been specified. So you have historical data, you have a lot of features, and then we label them initially. For instance, here we already know that the first person repaid the loan, the second person also repaid the loan, the third person did not repay the loan. So this data is for 3 people. They are called observations. You could have millions of people, millions of customers, and you could populate their data with the label that is whether they've defaulted or not. And then our machine is going to use this data to understand the relationship between this label and the features. Next thing that I mentioned in the previous slide was you might also need to split your data into a training and a test set. Now, what does that mean? So let me again take an example, analogy. For example, if you ask a child to memorize certain like math equations, and then that child memorizes just 2 equations, maybe they're just 2 equations in a hypothetical book. So 1 + 2 is 3 and 1 + 3 is 4. And so the child goes to the school and he gets a test. And in the test, the question that the child gets is similar to the one that the child had studied. And so the child is very confident and he answers it. 1 + 2, yes, it's 3. And he gets good grades. But suppose the question was changed. And the question that was asked was very different from the one that the child had studied. And since the child had no clue about that question, the child performed very bad. So this means that we should always generalize the problem. And this means our machine learning model. So if you would change this entire scenario and you consider this to be a machine learning problem, you don't want your machine learning problem to only work well with the data that you have fed into it. It should be able to give equally good results for any unseen data. So for instance, you have used the historical data of all the customers in your bank and you've created a model. Now, next time when a new customer comes who's migrated from a different country, say, and you do not know about that person. Now, when he applies for a loan, your machine learning algorithm should be able to predict equally well whether that person will default or not. This is called generalization. So your model should be able to generalize on a wide variety of data. And to evaluate how well this has been done, it must be tested on an independent test data. And if you don't have that, you should separate your training data in some ratio like 80-20, 70-30 before you start training your model. And you should keep that set aside, and then you should evaluate your model on that data afterwards to see how well your model performs. So we've gone from the data science workflow, and we've talked about the features and labels. We've talked about training and test set, but there's also another aspect, that is the next phase is analyzing that data that you have got. Now you've got a lot of data from different databases and you've populated it. Now you need to analyze what that data contains. And you might even want to do some feature engineering. You might want to reduce some features. If you think there are some features which do not add any information, or you might want to add new features. So the data analysis portion is called exploratory data analysis. You explore the data through some visualization libraries and you see a pattern, what it is, what information it has. And this is again a very important part of your machine learning workflow. Feature engineering. Again, feature engineering is a vital part and it's a very important part of the workflow. And what does it mean? So feature engineering is about creating new input features from the existing one. So how do you do that? So again, for our example data set that we have, what I think we can do is we have 4 features with us. What if we could create a new feature called payment pending? And that could be obtained by subtracting the bill amounts and the payments made. So with this, we get a new feature, and this gives us an idea that how much payment is pending for a person. And because maybe if more payment is pending, the person is not going to return the loan amount. And if less payments are pending, he might. So this could have a correlation between the variable that we are trying to predict. And similarly, we could create multiple features, and then we could test how our model is performing. And then we could iterate back, we could remove the features, we could again add new features, and so on. But feature engineering is a very, very important step in any machine learning workflow. And this is a very good, I think, it's a cartoon actually, which tells you about the importance of data cleaning and data preparation. So it said that on an average, a data scientist spends about 80% of the time on data cleaning itself. And that is even true. Even though this is the most boring part, but this takes a lot of time. And even though modeling and using the algorithms looks very nice and everybody wants to jump on the modeling part, you have to be sure that your data, whatever you're feeding into your model, it's clean, it has been prepared, and it's fine, it's good, because whatever you're going to feed in there, you're going to get the similar thing as outputs. And so some people have this tendency of immediately resorting to the modeling part, and then they get bad results in the end. And then they go over and start checking what is wrong with their data. And then they find some inherent problems, like there's biased data, there's unbalanced data, and so on. So we've gone through the first and second part. Let's come to the part of training a model. We have briefly touched on the modeling part initially, or the learning phase, but let's look at what does model training mean. So model is nothing but it is a mathematical representation. You could say it's a code, a business logic. And the general idea is that we create models and then we feed data into these models to generate some outputs. So these outputs might be like, for instance, predictions for future trends or some patterns in the data. A model in itself is a self-contained package. So that takes in the features that has been computed from the input data, and then it produces a prediction. Now this package or the model can take many forms. It could be of a variety of forms, but it always includes a mathematical representation or a code. Now, when we use a model, there's always an underlying assumption that there is some pattern that we want to measure, but it has some error on top of it. And a good model will look through that error to find the pattern. So that is why how you decide which is a good model and which is not. Now, there's a very important thing to highlight here, and one common problem when beginners especially work in data science is the confusion between what is a model and what is algorithm. And sometimes I've seen somewhere people use it interchangeably, but it's not. So, like I said, an algorithm is a set of rules. So it's a set of rules, and that is to be followed to reach to a certain conclusion. For example, there are regression algorithms, there are classification algorithms. A model is what you build using an algorithm. So a model will always represent what is learned by the machine learning algorithm. So for instance, you create a model to classify males. You create a model to identify which person will default or not. You create a model to predict what will be the sales after 30 days. So if you were to put it into a formula, it would be something like this: building a model using a given algorithm. So next time, whenever you should say it like this, that you need to build a model by using a certain algorithm. And so model is algorithm when you feed data to that algorithm. So with this, we come to the last part of the workflow. That is, once your model has learned, yes, you need to understand what it has learned, and you need to explain it also. So explaining means you need to explain your predictions or your answers to a lot of people, your stakeholders, because they are the ones who are going to take decision based on your model's predictions. You also have to explain it to the regulators, and this forms the crux of responsible AI. So today, machine learning models are no more black boxes because we have algorithms, we have things in place which can explain, for instance, why a person was denied a loan or why another person was given a loan. And it becomes very important to be able to explain your predictions because that forms a very important aspect of the trust factor in artificial intelligence and machine learning. And also, today, a lot of regulatory bodies, including the healthcare and financial institutions, they require the companies to explain their decisions because they have implications. Because these models are, the predictions are now used to decide for humans. And once you understand, once you are able to explain, then you deploy it. You deploy your models into production. And you make it available as apps, you release the APIs so that people can use it. And then you have to constantly monitor because the data is coming, new data is coming. You might have to make changes to your models. After some time, you have to make sure you just cannot leave a single model there and forget about it. And so this forms the iterative process. And so you have to evaluate your models on some of the metrics. You have to see whether your models is actually performing well or if its performance is deteriorating with time. If putting a larger training data, maybe. So when you started creating that model, you did not have access to large amount of data, but after some time you had access to some sufficient amount of data, and now you think whether this will improve my performance. So you start the training phase again. Again, the bias aspect or the ethical aspect of your model has also to be kept in mind. So the workflow that we saw, it's a very simple workflow. And like I said, this is not what actually seen in the industry. And what actually seen in the industry is something like this. So this is this entire life cycle. And you see there are multiple parties involved here. There are multiple processes that are taking place. And each part is dependent on the result of the previous part. So for instance, you have data engineers. They will explore, they will augment the data, they will bring data from different databases. And once they have the data, they would pass it on to data scientists. Data scientists would then experiment and create models and work on getting the best outcome from the models, and they would then pass it on for deployment and testing in production. So there you have the DevOps team, you have the data ops engineers whose work is to actually deploy them into production and also maintain the production life cycle, manage the production life cycle throughout. Further down the line, you have application developers. So once your model is a good model, it's an accurate, it's good in giving good results, then you need to have an app created, maybe an app deployment, so that other people can interact, because people will not be able to interact with the model in the production. So you need to create an interface for the business users. And then this application developers, they develop it as an application, as a front end, and they create dashboards and other sorts of things which make it simple for the business users to interact. So what will the business users see? Yes, we had a problem, and now we have a simple solution in the form of an app, and we can use the model without having to worry about what goes on the back end. And business users, they use it for their own use cases, and they might have many use cases, and this is the whole life cycle that works. Now, this is not linear. Even though it's a circle, there are other issues that might creep in. So for instance, during the model development, you feel that the data is not sufficient, or you need to augment it more, you need to clean it more. So they will send the data back. So they would again, the data engineers would again be fetched in, and another cycle forms there between the data scientists and data engineers. Again, there could be more data available. Again, when your model is in production, it might fail the testing, it might again go back to them, and again, another circle forms here. And maybe from there, the model itself fails, and the model isn't giving such good result now. So again, that passes on to the data scientist to experiment more. And again, from the app development, also it might go back to data scientists to say there are some issues, or maybe they need to change. We could try another model. Maybe the accuracy has diminished over time. And again, so this, you could say, this is the actual life cycle that happens, and this is an end-to-end life cycle. So this isn't linear that we most of the time see. It's actually related, and every part of it is dependent upon the previous part. And this actually is the work of the entire team, and a lot of people and stakeholders are involved. And with this, I finish the last part also of my session. So just a quick summary of what we covered. So we understood what machine learning was, what kind of problems or how the problems could be categorized, classification, regression, or groupism, groups or clustering. What are the important components of machine learning? Data, features, and algorithms. And then all of this together into a machine learning, end-to-end machine learning workflow. So this was all that we covered today. And the next session will be on the types of machine learning, about which I gave a little hint about supervised, unsupervised, and reinforcement learnings. They have different kinds of algorithms which are used. And we'll take the session on next Tuesday, the coming Tuesday, in the same time. But if you have any questions or suggestions or anything that you want to ask related to the last two sessions, this and the previous one, you could join us on Saturdays and Sundays, and we'll be more than happy to help you. And with this, I conclude my session for today. I hope you've enjoyed it. Thank you.
Parul, thank you very much. Parul, we have a little bit of time. Are there any folks who have questions? You can kind of put that into the question and answer, or into the chat. Okay. It seems like things were pretty clear this morning. So thank you very much, Parul. And we will see you either on this weekend on the optional study group sessions or next Tuesday. And the replay and slides will be posted within 24 hours. So thank you very much. Have a good day. Oh, I guess there's one question, Parul, before we come here. Do you see it?
I cannot see it. Okay.
So how to differentiate between classification and clustering?
Yeah, so classification basically entails differentiating into categories and there you know the historical answer. So you already know, like for instance, you already know whether your data set belongs to either of the two categories. Clustering, you have no idea. The data set that you have has no historical knowledge. You don't know. It's just given to you. Look, this is a data set and see what you can do with it. So this forms the basis of unsupervised machine learning, which I'm going to cover in the next session. But for classification, you should have some of the historical data. You should know prior knowledge about what this kind of data is. And more will be covered in the next session.
Okay. I'll do one more call for questions and then we'll wrap up. Okay. So thank you very much for joining again. And we will post the slides and the replay within 24 hours and hope to see you at the next our next session. Thank you. Have a good day or good evening.